Hello. We're going to continue discussing the classic 1983 Lucas-Stokey paper on optimal taxation. This is a beautiful paper in several senses. They did a very clever job of stripping off many inessential things for the purposes that they were aiming at. For example, capital, and including things that they wanted to focus on. In particular, state contingent, complete set of state contingent markets. Okay, so I'm going to use as the text for this the quant econ lecture that we were using last time, and I'm going to continue with the recursive formulation. On the Google group, I've put chapter 16 and chapter 20 of Recursive Macroeconomic Theory, edition 4. What I'd like you to do is in chapter 16, just look at the parts on the Lucas-Stokey model. And I'd like you to spend some time on section 16.13, which contains 3 examples. And understanding these examples will help you stress the sensitive parts of the Lucas-Stokey model. Okay. So Lucas-Stokey model, there was no capital. There's a simple technology. Labor supplied produces output 1 for 1. There's an exogenous stream of government expenditures that has to be financed. And at the end of last lecture, we specialized the general setup we had to make the government expenditure process be Markov. And we're going to continue that specialization today. There's a representative consumer who likes to consume and doesn't like to work. There's a Ramsey planner or a government that can finance the government expenditures in one of 2 ways. It can levy a flat rate tax on labor, which is distorting. It's a flat rate tax because Lucas and Stokey impose it as a flat rate tax. The tax can depend on time and it can depend on history. In particular, it can depend on the history of the Markov strait that drives government expenditures. The government can also buy and sell a complete set of Arrow de Bruce securities. Actually, in a formulation that we're going to use today, we're going to use the Arrow security form. Okay, so what we're going to do now is we're going to use something that we encountered in chapter 19. We're going to Bellmanize the Ramsey problem for the Lucas-Stokey model. I'm going to follow procedures very similar to what we encountered in the linear quadratic setting in chapter 19, except now our problems aren't going to be linear quadratic. In particular, we're going to break the Ramsey problem into 2 subproblems. And the structure, the logic of the problem forces us to do that. The fact that there are these 2 subproblems is going to tip us off to the fact that the Ramsey plan is not going to be time consistent. That's a feature that we saw last time. And the way it surfaced last time was the first order conditions for the Ramsey problem in the sequence formulation that we used were different for times t greater than or equal to 1 vis-a-vis time t equals 0. And there was an additional term in time t equals 0 that's going to come back and visit us today. So you should keep your eye open for how that additional term is going to surface when we formulate things recursively via Bellman equations in two subproblems. So the deal is, we're going to think about a Ramsey planner at time 0, and it's going to be followed by a sequence of continuation Ramsey planners. So a continuation Ramsey planner has different purposes, a different objective function, and has different constraints than a Ramsey planner. And those differences are going to give rise to are going to express or represent the time inconsistency of the Ramsey plan. Okay, and we're going to use a trick that we encountered last time. We're going to define a state variable, which is this thing we called X, and what it is, it's government debt, which is due in state ST at time t, and we're going to scale it by the marginal utility of consumption. So this is going to be marginal utility scaled government debt. And we are backing ourselves into defining this as a state variable by a logic that we described last time in our last lecture, in that this state variable xt played a critical role when we stared at the implementability conditions for the condition for the Ramsey planner. Okay, so here we go. So what's going to be true is that a continuation Ramsey planner is going to face xt as a state variable. And what it's going to choose at time t, it's going to choose a CT-NT pair, and then it's going to choose a xt plus 1 state contingent on st plus 1 for next period to hand down to the next continuation Ramsey planner. That's going to be the idea. So the deal is xt is a state variable for t greater than or equal to 1, but it's not a state variable at time 0. And in particular, x0 is going to be partly chosen by the time 0 Ramsey planner. So this is going to be chosen, and this is going to be not chosen. And that's going to be the key difference. So as last time, this xt is going to be both a forward-looking and a backward-looking variable, if you like that MIT language. So here we go. So let's see the two Bellman equations that we're going to be working with. And again, please be on the alert for how this is going to resemble what we did in chapter 19 on dynamic Stackelberg plans. Okay. So we're going to have two subproblems. And as usual with dynamic programming, we're going to say let is going to be always our first word. So we're going to let v of x and s be the continuation value of a continuation Ramsey planner. And he's going to face state xt equal x and st equals s. And something we're going to ask along the way is this in some sense is a subtle question. The sense in which x and s are independent state variables. Put a question mark there. They are, but there's going to be a sense in which they aren't, although they really are. Okay, we'll clear up that mystery soon. So the second thing is we're going to let W of B and S be the value of a Ramsey plan at time 0 when initial government debt is B and initial state is S. So the key thing, one thing to notice here is the arguments of the Bellman equation for the argument for the value function for the Ramsey plan is distinct from the arguments of the value function for continuation Ramsey planners. Again, this mimics chapter 19. So we're going to work backwards as usual. And first we'll look at the Bellman equation for the continuation Ramsey plan. So here it is. V of XS is going to be the maximum. So what's the government? I've substituted out consumption by using feasibility. So this is consumption, and this is leisure. So what the Ramsey planner chooses, the continuation Ramsey planner chooses at a particular date, he chooses employment, and he chooses a set of continuation X's to hand on to the next continuation Ramsey planner. And this is the utility of the representative consumer today. And this is the discounted value of the continuation utility tomorrow. And here's our Markov chain, transition matrix. So we're going to choose and we're going to choose the S elements of this. And we have a single implementability constraint. Our implementability constraint is this object that we last time said looked like an asset pricing equation. Today's X is equal to this plus beta times that. And remember, we said this looks like an asset pricing equation. Actually, it looks like a very simple asset pricing equation, the kind that Schiller used back in the 70s and 80s to talk about volatility puzzles. And part of those puzzles were that he was using a very simple asset pricing equation. Okay, so that's our Bellman equation, and we're gonna solve it. And later in this lecture, there's Python code that solves this. Okay, so then we can just pedantically look at what the policy functions are that attain the value function. So stare at the policy functions. What's being chosen is for every X and S that you come in with, the Ramsey continuation planner chooses an employment today, and then he chooses a continuation X for tomorrow. So given X, T, and ST, for each ST plus 1, he chooses an XT plus 1. So this is what's being chosen. So that's all that a continuation Ramsey planner does. And when we take classes on computational economics, we learn how to solve equations like this. Okay. So then now we go to our second subproblem, our subproblem working backwards for the Ramsey problem itself. So the Bellman equation for the time 0 Ramsey planner, it's kind of redundant when I say that, is this. The value of the plan today is going to be the maximum. Look what the Ramsey plan, so B is taken as given. The maximum is choosing a employment today and a set of continuation x's tomorrow that are going to be functions of next period state. He's going to choose one of those for every possible next period state. And his value function tomorrow is not w, but it's v. And it's the v that was imported from up above. Okay. So the time zero value function depends on this is for the Ramsey planner. And this thing is for the continuation Ramsey planner from our first subproblem. By the way, if you ever study hyperbolic discounting of the kind introduced by Phelps and Pollock, used extensively by Leibson, the Bellman equations will often look like this for different reasons. And the time inconsistency will, under hyperbolic discounting, will emerge for exactly the same reason technically, because there are these two subproblems. Anyway, that's a digression. Okay, so now that's the Bellman equation, and the implementability constraint, the time zero implementability constraint is now this. The key thing here is x0 is not given. So look how we wrote the implementability constraints up here. We took x as given. And here, x is not given. Instead, v0 is given. And if you'll note, by choosing n0, one affects the marginal utility, you see, is going to be a function of n minus g. So by choosing n0, one affects this term right here. So this is manipulated. The Ramsey planner is taking into account how its choice of employment today, and therefore consumption today, influences both the marginal utility of consumption, which appears here, and the marginal utility of leisure. That's all taken into account. Whereas here, in the continuation Ramsey planner, it's taking into account how the marginal utility of consumption is affected by those things, but X is locked. You cannot affect X. That's the whole trick here. So that takes a little digesting. It's not obvious, and it's actually a very clever trick that was first recognized by Kidlin and Prescott in a 1980 paper. Okay. So associated with the value function that solves the Bellman equation, there's going to be s+1 policy functions that look like this. And notice the policy functions are differ from those of the continuation Ramsey planner. Okay, so that's how we formulate this. The value function of the continuation Ramsey planner, well, is just the value of the continuation discounted stream of the utility of consumption and leisure. Okay, so we can do a little technical work here, which I'll ask you to look at. We're just going to get some first order conditions for the continuation Ramsey plan and for the Ramsey plan. And we're just going to proceed in the usual way. We're going to put a Lagrange multiplier phi1 on the implementability constraint facing a continuation Ramsey planner. Do a little manipulation. Use an envelope condition. I'm going to let you go over this. And then we're going to do the same thing for first order conditions. We're going to put a Lagrange multiplier phi0 on the implementability condition for the Ramsey planner. And we're going to get envelope conditions and first order conditions. And then again, what we're going to note is that, well, the first order conditions are going to match up with what we got in the sequential problem. And except and they're going to differ. The first order conditions differ at time 0 and times greater than 1, except in 3 special cases. And the 3 special cases are: there's no initial government debt. And I will notice that in section 16.13, B0 is set 0 for all 3 examples. And that is going to simplify things. It's going to simplify things, and it's going to simplify the paths, and it's going to avoid, okay, it's going to simplify things. How? I'll let you think about that. Another special case is UC is constant. So there's a preferences are quasi-linear in consumption. Marginal utility consumption is just a constant. And the third one is that it turns out that phi is 0. The Lagrange multiplier on the implementability constraint is 0 because initial assets are so large that all government purchases can be financed with interest from those assets. So these are extraordinary special cases, and in general, the first order conditions are different at time 0 and at time 1. Okay. So, oops. Okay, so now I'm going to revisit about the question is, in our problem, are X and S independent state variables? Well, they are in the sense that it's imperative that both be entered into the value function as arguments of the value function of the continuation Ramsey planner. There's no question about that. Now we're going to ask, along the Ramsey plan, are they independent? Not off the Ramsey plan, but on the Ramsey plan. That's what we're asking. So what we'll notice is that simple argument, which you can go over and has gone over in the readings, the Lagrange multiplier on the implementability constraint for the continuation Ramsey planner and the Ramsey planner are going to have to be equal. First order conditions imply that. So what that means is that we're going to get this condition that if we take the derivative of the value function, and I'm praying, and taking for granted here that that derivative exists. And as you know from the Benveniste-Shankman and associated arguments extended by Santos, that's something that has to be demonstrated and can be under certain conditions, may not be true under others. But we're going to take it for granted. So there's going to be a casual argument. That for our problem is going to turn out to be okay. So I'm going to just notice that some of our first order conditions imply that as usual, kind of an envelope-like condition, the gradient of the continuation Ramsey value function with respect to x is going to equal the Lagrange multiplier in the implementability constraint. And this is a constant. So when v is concave in x, this is one equation that we can think of solving for xt as a time invariant function of st. After all, that's what the Ramsey planar chooses. So along the Ramsey plan, xt turns out to be, because of the activities of the Ramsey planar, we've seen this in another way, an exact function of st. So along the path, a time series econometrician might just say, well, there's really only one state variable, st, because xt turns out to be an exact function of this. So that insight helps us with some representations. Okay, so manifestations of time inconsistency, it often goes hand in hand with Ramsey problems. And this is the one-liner. Okay, so, and in terms of economic meaning, the time zero Ramsey planar and the continuation Ramsey planners have different obligations. They're solving different problems. They care about different things. So the continuation Ramsey planners are fictions that we've used to conjure up a sequence of continuation problems that allow us to use dynamic programming despite the time inconsistency. So the time zero planner has to honor government debt B0, but he can manipulate C0. The time zero planner can manipulate the value of that government debt measured as in margin utility. The continuation Ramsey planners are prohibited from doing so, and we must prohibit them from doing so in order to Bellmanize this problem. Okay. All of this has some implications about aero security prices. They turn out to be the same functions at every t. So with this Markov assumption about the state driving government expenditures, we get some nice properties. Okay. So now what I'm going to do is show you one of the examples that's in the QuantEcon lecture. And this is a slight generalization of one of the 3 examples of the Lucas-Stokey model at work in section 1613 that I asked you to look at. The only reason it's a little extension is those examples all set B0 equal to 0. Here I'm going to set B0 not equal to 0, and that's going to give rise to something that I want to focus on. And what I'm going to do is I'm going to use a trick. This is yet another instance of finding the state of an art is an art, to map something that at first sight might not look Markov into a Markov process. This is done in an exercise in chapter 16, but we'll also do it here. So here's the deal. Actually, I think it's done in an exercise in chapter 20 instead. Okay, here's the deal. Government expenditures are, we're going to activate a Lucas-Stokey model by making up a stochastic process for government expenditures. We're going to make up a very simple one, as is done in all of the examples in section 1613 of the RMT chapter. So the deal is government expenditures are known for sure in all periods. So 0, 1, 2, 3, 4, 5, except for one period, and that's in period t equals 3. And in period t equals 3, there's going to be a war that occurs with probability 0.5. So if there is a war, government expenditures are twice the usual amount in period 3, only for one period. If there's no war, they're just what they usually are. And we put in values 0.1 and 0.2 because we're going to turn on Python. Okay. So now we're going to define a state variable, S. And there's going to be 6 values of it. So what we want to do is we want to map this setting. The whole trick we're going to use is we're going to create a state space S. We're going to have S belonging to S. And we're going to include a transition matrix. This is what we want. We're going to use the want operator. We want this. We want to find a state and a state space and a transition matrix that captures this description. So here's how we're going to do it. We're going to define components of the state vector S as consisting of date government expenditure pairs. So the pairs are going to be, the first pair is, this is going to be state 1, this is going to be state 2, state 3, and so on. 1, 2, 3, 4, 5. There's going to be 5 of them, if I count right. Oh, there's going to be 6 of them. Which I'm grouping a whole bunch. So the first one is going to be the pair time equals 0, government expenditures are low. Time equals 1, government expenditures are low. Time equals 2, government expenditures are low. Those are the first 3 states. The transition is going to be, the transition matrix is time is going to advance, so you're going to move from state 0 to state 1 with probability 1. I'm sorry, you're going to move from state 1 to state 2 with probability 1. You're going to move from state 2 to state 3 with probability 1. Once you're in state 3, you're going to move from state 3 either to state 4 or to state 5 with probability 0.5, and so on. That's what we're doing. And if you check that out and do a little thinking about it, you'll see that this transition law and this selection of the states captures that expresses that particular stochastic process for government expenditures. And then we just make up a list of government expenditures in each state. There are 1 in every state except this one. These 2 states share the property that t equals 3, because look here. T equals 3 is here, and t equals 3 is here. It's the only, okay, so you see how we do that. So we're actually doing some pseudo computer coding. We're writing pseudo computer code, which you always do before you actually write computer code. So then we're going to assume that the representative agent has this utility function. We're going to make it time separate. We're going to have these two power functions. And we set the discount factor. So we've completely specified a Lucas-Stokey model now. This technology is timed down. Oh, okay. And we're going to set initial government debt at 0. Okay, so then what we're going to do is I'm going to show you some pictures where we computed the Ramsey tax. Government expenditures. Okay, let's see what we get. Okay, so black is going to be, it's going to be no war. Red is going to be the war. So now we're going to show a bunch of stuff. Now, how did we compute these? Well, and I'm not requiring this. I'm not even, it's completely optional. It's not the subject of this course. The Python code is all there. Python code looks very close to pseudocode. So one way, we computed these things two ways. One is sequential, the last lecture. And in the last lecture, I showed you how to solve, I forgot how many equations, something like 2s plus, I forget the number, 3 equations. And then we solve for a phi. That was our algorithm. Solve a bunch of linear equations and iterate over phi. The other was we're going to do it recursively and solve it pairs of Bellman equations. The code does both of those. Guess what? It gets the same answers to machine accuracy. Okay, so here's what. Remember, black is there's no war that occurs. Okay, so what we have here plotted is the consumption for the Ramsey plant, labor supply, government debt. Well, that government debt is B. It's BT. And we're starting off BT equals 1. Here's the tax rate. And here's government spending. It's always 1, except in the when there's a war, the red one, it's 3. It goes up in period 3. It goes up to 2. And here's output. Output is going to be a copy of labor supply. Okay. So if you look at section 1613, there we had B0 equals 0. And I'll show you what happens then. If B0 was 0, both of these lines this would be totally flat. This would be totally flat. This would be totally flat, but it would be at 0. It would be at 0. It'd be totally flat. The tax rate would be totally flat at a different level, actually a lower level because we'd have that. And these other two would, well, this would be totally flat too. That is if true if B were 0, but B is not 0. So this is what we get. And now something's going on here. Okay, so what's going on at time 0 is when we solve the Ramsey plan is the government is manipulating the value of time 0 debt measured in marginal utility units. And if we look at this, what it's actually doing is, so look what is, the tip-off is what it does to the tax rate. It actually lowers the tax, it uses a lower tax rate in time zero than it does in any other period. The consequence of that is labor supply is higher and consumption is higher. So people are intertemporally substituting, they're working more. So consumption's higher and they work harder. When consumption is higher, it actually lowers the marginal utility of consumption, and that lowers the value of initial government debt. So the government is tailoring the tax rate at time zero, partly with an eye to manipulating this object. Now, to see that a continuation Ramsey, a continuation of a Ramsey plan is not a Ramsey plan. If we started, you can tell that, you can read that from this figure. I'll leave that remark a little mysterious. Another thing you know is because the government has lowered the tax rate relative to what it's going to be in a steady state, the government actually issues, it actually has to issue, increase the amount of debt. It runs a net of interest deficit between period zero and increases its indebtedness to the public. Again, that's all a part of this Ramsey plan and the manipulation of this object here. Okay. And then the tax rate is entirely flat here. And then the paths for the fact that the tax rate is perfectly flat here is interesting. And I think what I want to ask you to do is think about, so what the government's doing is it's actually issuing right here in period 2. It's really interesting what happens. So from this graph here, we can read off the state contingent government debt that's being issued. So how can we do that? So the government comes in with this debt that's inherited from last period, at period 2. And now what it does is it issues state contingent debt. It actually, that is going to pay off. So the government's going to have to actually increment its debt if there's peace. But if there's war, the private sector is going to be compensating the government for that. So if there's war, the government indebtedness goes down. And then once the war ends, the government debt in the war, the way the government is going, how is the government going to finance the war? Well, we can tell how the government's going to finance the war. If there's a war, its initial debt has gone down. It's not going to change taxes. It's not going to change taxes. But what it will do is issue a bunch of debt. So its indebtedness goes from here all the way up to here. And that's war finance. This is war finance. So we can deduce all this from this picture. And now, during the war, the labor supply goes up and consumption goes down. And this is a consequence of the big increase in government expenditure. So government expenditures go up. There is some consumption smoothing response because while government expenditures go up from 1 to 2, consumption takes a hit, but it only goes from 0.89 to a little over 0.84. So it doesn't go down very much. The labor supply goes up a lot in order to produce more. So output goes way up during the war. So that's the deal. So we can read all of these things from this graph. So that's how we computed things. We can figure out what the interest rate's doing. The gross interest rate on risk-free debt is given by this equation. And we can back out that interest rate by staring at these graphs. Okay. So this is what the gross interest rate does. This is the gross interest rate on risk-free debt. The gross interest rate for one period risk-free loans. And it moves all over the place. And its movements are dictated by consumption movements. So again, the red is peacetime and the black is war. Okay, so we can back out, we've already done this, government saving. And the reason it saves, well, we discard that. Okay, and again, all of this is, there's a big element of time zero manipulation of the interest rate here. So by raising this interest rate, the government is having an effect on consumption. So once again, I think we've talked about this enough. The tax rate, the telltale sign of time inconsistency here is the tax rate differs from its value at 0 from other times. The QuantEcon lecture has some discussion of this and some comments about it. So I'll let you look at this, and so now we have, since we have this Python program, we have a machine for studying many other examples. So if this was a class in computational economics, I'd give you some more exercises where we had more exciting government expenditure processes. But I might point you to how we did when we changed from CES preferences that we had before to non-CES preferences. Some of these things change, and we have graphs of this. But I think this is all I want to say today about the Lucas-Stokey model. If my experience is any guide, it took me a long time to get inside the Lucas and Stokey model. There's a lot going on. There are subtle interactions, and there are the interactions involve the motivations and the authority and of the Ramsey planner and the continuation Ramsey planner and the best responses of the private sector. So if you're like I am, this might deserve a little time. This is a classic model. that forms the basis for lots of subsequent work. So I think time spent pondering it will be well spent.